Would I use this library? Perhaps. I think this library is for folks who want to get more into signal processing. They may have NIR data or FTIR data or something similar and may not know all the techniques off the top of the head that they want to use. And this library sort of gives a nice repository of that information. Welcome back to the channel. Today's video, we're going to take a look at the Nippy Spectral Processing Library. This was a library that was brought to my attention by a YouTube commenter that recommended that I check out this Nippy library. So in part one of this series, I looked at the documentation and got a better understanding of some of the layout of the data, enough to explore it a little bit. And now in this video, we're going to explore it more programmatically in our own Jupyter notebook. And so I have created a Nippy environment. And so I duplicated my base environment and added Nippy to my Jupyter, Pandas, Plotly, my normal data science environment. And so just in case something else goes wrong or I need to update some libraries, I don't impact my base library. So ensure you do that, especially when exploring new libraries that are very different. And in this case, we're going to also look at some of the Nippy data. And that's because I want to understand how these libraries work based on the data structure they've given us. And this is a near infrared spectroscopy data set. We could find that data in the examples NIR CSV file. And so we have this GitHub blob, and we can see that we have a URL to this data set. And this is that data table. And so I have already downloaded this data into my environment. If you want to download it too, just use this icon over here on the right side of the screen, and we can begin processing. In my notebook, I have Nippy, Pandas, and a couple of plotting libraries, as well as warnings, because there are some warnings that might pop up with this notebook environment that I've created. And of course, this config line to ensure we have a high resolution figure for your viewing pleasure. And now I am ready to read in the data. So this data is stored in the same directory as this file, so I can access it using this short form, nar_data.csv. The data set is a comma separated file, a comma delimited file. So if we were to change that delimiter, you can see we completely changed the data structure. So this allows me to be pretty confident that we have the data set structured properly. And so let's begin. And so looking at the data structure, the column headers are the wavelengths, and each row represents a sample. Now, there are no sample IDs, so we don't really know what we're looking at besides this just being sample 1, sample 2, sample 3. And we will just go from there. We'll pick a random sample. And the primary goal of this data is just to help us understand the Nippy library. We have other NIR data that we can explore, but let's just take a look at this. So back to our Nippy notebook. Let's run Nippy notebook. So back to our notebook, let's run the first cell and ensure we have all of our variables imported and put this data set in our environment. Now, one thing I did have to do was to convert the columns to a float data type. Without this, if I were to comment this out and look at NURSDF and the columns attribute, the columns come back as an object where we can visually determine that this is a numerical representation. And so to ensure that I am just using this columns as type float, and I could change the data type of the columns to a float point. And so now we have our wavelengths. We have data with a resolution of about 6 nanometers. That's pretty typical for what is probably a small near-IR source. And so we could take a look at this data. The other thing I want to do is just pick a particular spectrum. So I don't necessarily care to explore this full data set because I don't know enough about the samples. So let's just choose a random row and look at this data. So let's just call this spectrum. And we'll use NURSDF and the loc method, and we will just search, let's say, rogue 15. And when we look at this, we will return a series, name 15. And this is primarily just for plotting purposes and to allow us to look through this Nippy library. And so we have our data. Let's plot it just so we can understand where we're going to begin with this. So plt.plot, and we can just plot this series. We look at it. So I'm an analytical chemist, and when you see these flat tops, It very likely means you're saturating the detector. We're losing some information because we don't have a response higher than that. And so, of course, I would, if I were running a real experiment or if this were my data, we would be adjusting the concentration of the samples down to ensure we have some linear response or at least attempting to correct this. So again, this is just sample data produced by the authors of this library. And so we're just going to use it. Again, we're not doing a full exploration. We're primarily focusing on the library. So we'll just leave it at that. Okay. So we've pretty quickly generated a spectrum, and the y-axis would be the intensity. The x-axis are the wave numbers or wavelengths. And we have some data that appears to be saturated on the high end. But we also can make a number of other observations, such as we can see that the baseline is not flat. So if I were to plot an x line at y equals 0, we can see that the baseline is not flat at all. And let's just adjust the color to red. This helps us to sort of get an idea of where we are from the baseline perspective. Not that we necessarily expect the baseline to be at 0, but we can see that there is a slope up. And so let's attempt to correct that using this Nippy library. There's a couple of approaches we could try. So let's use the dtrend function, and my alias for Nippy is n. I import Nippy as n, so I will access it using that alias. And we will use the dtrend, and it shows that we just pass in our spectral data, and we can set a BP, which are breakpoints. And so let's pass this in and see how well this goes. There's not extensive documentation for this library, and so when you consider how you might want to contribute to certain packages, this is what, and sort of an easy way to get in is just to improve documentation, add more examples. When you compare this documentation to that of, let's say, pandas, so PD dot, let's choose let's use spectrum. Let's just get a series method, and let's just choose one randomly ag. Here is a professionally documented function. You can see we have the parameters, some function, we have our arguments. There aren't many in this case, but it also tells us what the return variables are, other ways to use it, some notes on the activity, and examples. So this would be very helpful for this particular dtrend, and I'm sure many other methods in this library for us to better understand what we should actually input. It definitely shows an NP array, but it doesn't necessarily give us much more than that. And so and that the BP should be a list, a sequence of breakpoints. And so let's see how this goes. So let's set our dtrend. We'll just pass in spectrum, and let's just set a single breakpoint. So breakpoint equals 2. And we will return a new array of values. And I don't believe this updates our spectrum, so it returns spectrum. So I don't necessarily think that's the case. So let's call this dtrend, or let's call this new spec. And I want to plot this data so that I can better see what's going on. So let's set sns.line plot, and let's set y equal to new spec. And if we plot just this, let's set our data is set to new spec. So the line plot first entry is data. And if we set just this, you see that it takes in, it's assuming that these are the intensity values, are the y values, which is the correct assumption. And our x values become just the index values of that data. And so what we really want to do in this case is let's just specify y as new spec and x as spectrum. That's our original data dot index. And so now we've adjusted to ensure that we have the right index values. And the reason we're going to do that is because I want to compare this new data. So let's call this label equals new spec and to the original data. And I will just pass in our plt.plot spectrum. And so we have our new spec data, which is this blue trace, and our original data, which is this orange trace. You can see that the orange trace, again, has that positive line up, and the detrended data, which we've just set a single base point, has sort of an adjusted curve down. Now, it says that we can pass in our breakpoint as a list, and so let's set a breakpoint at 100 and see how this impacts our data. And maybe it does slightly, but you can kind of maybe, I think this feature here is new. And so it's establishing a new point from which to establish where the baseline is, and I think try to adjust it. I don't use detrend very often to adjust my baseline. There are other approaches I tend to prefer, but we can just see how this works. And it is convenient having these methods called out, but because the documentation is a little bit more challenging to understand how to use this library, but it does, like I said, these tools are convenient. And so let's try something else. So let's look to see what other methods exist in the Nippy library. So in .nv, let's just try baseline, the baseline function. And again, it takes in an argument spectra and no other arguments, and it appears to just remove the baseline by computing the mean from each spectrum. And so let's just pass in our spectrum. And we get the baseline corrected values. So let's call this again, let's call this baseline spec. And I'm going to copy this code here. And let's save our time. We'll just call this baseline. And we have our baseline corrected spectrum. No, wait a sec. There we go. Now we have our baseline corrected spectrum. Didn't adjust the Y. And it now, you can see that we still have our slope, but the mean is now 0. So if I plot that horizontal line again at y equals 0, you can effectively see what it did. Let's set C equal to red. Now the mean value is set to 0. The mean of that spectrum is now 0. And because of that slope, we have our initial points below that point and our later points above. And so when you do have that trend in the baseline, just mean adjusting to a single point is not going to be sufficient. You definitely want to apply some derivative filter or some other detrender or other linear regressor to adjust the baseline and weight it properly so that you can sort of take that tilt out of your data. So mentioning about derivatives, let's see if there is a derivative method. I'm sure there is. Derivate, let's try that. And so let's look at the documentation. Computes the nth order derivative with the desired spacing using numpy.gradient. Okay. And so we can take advantage of that. I believe the argument, is spectra. So we're just passing our single spectrum. And we'll just take in the first order, but let's just create a variable called order, or let's use that argument and we'll just call it nth. And I'll just set nth equal to 1 in case you want to tweak that in the future. And the second is the delta, which is an integer, delta of the derivate in samples. I'm not quite sure what that means. We'll leave it at 1. I would have to go back to the source documentation to understand what they mean by this. But generally speaking, the derivative is the major component, or the order of that derivative is the key driver. But we'll just keep it there to keep it simple. So let's just call it deriv spec, and let's bring this in. So you can see that's just these two. So you can see how the data is now updated visually based on this transformation. So instead of plotting baseline spec, we're going to plot derive spec. And we're going to keep our x as the original spectral index of our data. and we're going to plot the original spectrum so we can see that difference between the derivative spec and the original data. Okay, so we now have our second derivative. I'm like, oh, it looks kind of strange. We have our second derivative. So let's first plot the first derivative. And when we run that, you can see how now we have our first derivative integration of those samples. And so where these peaks flat top there is no signal. And so that effectively goes down to 0, with the exception of some of these spikes. And then where we do have this broad peak, where that peak is increasing, we have a slight positive slope in our first derivative. And then as that peak goes down slowly, we see that it flattens out pretty quickly. This is where we probably need to combine a couple of different signal processing to sort of adjust the baseline, maybe smooth this out and get a better sense of the peaks. But because this data is not that great to begin with, I'm not going to get into that, but I do have a video on building out the signal processing techniques, and this Nippy library is just one way to do that. But SciPy has another set of techniques that are really easy, really convenient, work on data frames pretty readily, and achieve most of what this is doing, if not more. But again, we're just exploring this particular library for now. So let's see what else we want to do. And since I mentioned smooth, let's see if they have a smoother. They do. And it takes in a spectrum, a filter window, a window type, and a mode. Arguments, spectra, there's data matrix. Okay. Let's see what, I don't recall the earlier method saying data matrix. Okay, they do. Okay, so let's see what we can do here. So we have let's try to smooth this out. So it's not explicit with how it smooths. And we could go back to the source documentation and find that out. But again, some of these libraries include that as part of the examples and some of the explanation, but that's okay. What we want to do is let's pass in spectra equals spectrum. Spectra equals spectrum. It wants a filter window, so we'll set filter window of 3. And these are default to flat and reflect, so let's not worry about that. Those arguments there. And we'll call this smooth spec. And let's run that and see what we get. Get an index error. Tuple index out of range. For column in range, spectra.shape. Okay. So the processing is probably a little bit more complex than I originally imagined. So since it looks like it is expecting more of an array type. So let me comment this out and I'll work through what I think the solution might be. So spectrum for us is a series. I'm guessing because the shape of a series does not include the index. Yeah. We need to change the shape. And so to do that, let's convert this to a frame. Let's see if this works. And we've done this before. So the frame just alters the shape slightly. Where we now have the 243 rows and a single column. And then we can convert that back to a NumPy array by using 2NumPy. And we get this array here. So let's try this instead of our series here, which I said might matter because of how it's processing that data. And SciPy is expecting a slightly different data shape based on that original error message. So let's see if that worked. It looks like it did. Yeah. And it returns that shape back to us. Okay. So let's plot this data and see what we get. And we'll copy these plots just for consistency. SNS line plot. And so for Y, now we're going to just pass in smooth. Spec. And let's see if this works for us. No. Value error, pre-column Must be one dimensional. Wait a second. Let me check spectrum.index momentarily. Okay. I need to flatten this out. So my dimensionality is now just continues to be off. There we go. So now we have the data compressed right back down to a single dimension, which is what's needed for this Y argument there. And we have our smooth spec. Where is, I think it updated our data. It did. Okay, so all these used to be saturated and they're not anymore. So I made a mistake. I probably, and this is again where documentation matters. It appears, unless I've done something that's wrong, that is actually updated our data here. So what I should have done, and I now have to rerun everything, is used a copy just to make sure I don't impact the original spectrum data. And all the previous methods, it had not impacted it. So it was fine just running the method on this array. It returns a copy and I can save that copy as whatever. That is not, in this method is not the case. So let me rerun this and test that theory. So you can see how at the end of this spectrum, all of those data points should be at 4.0 or saturated. And in this case, they're not. So I just rerun everything. And yeah, there we go. So it does somehow overwrite. And with this copy here, it will save a copy of the object data. So that's important because we can avoid overwriting that when this thing returns, and we are good to go. So if we increase our window so it's more obvious, our smooth data is in the background. So let me set this alpha to 0.3. So we can see how our data is now smoothed. And this was the data that was originally overwriting our orange. But the take home from this library is that it is a good library and has a lot of convenient methods. The documentation makes it a little bit hard to explore, but it does appear that there are a lot of preprocessing functions, EMSC, a local standard normal variate. So lots of things that we can continue to explore with this, especially if you're unsure of the techniques that we could apply. Now, there are ways to easily access this using SciPy. Some of these things using SciPy or building your own. I have a number of videos where we built some of these preprocessors. But nevertheless, a good library. I haven't checked the accuracy of these algorithms, but if you want to go through and look at the documentation, feel free. I think this was a great exploration. So thank you for suggesting this. And I hope this was helpful. And in any case, I'll see you in the next video. Peace.